So now we're going to talk about the operation of addition. And with all of the arithmetic operations, our goal is twofold. First of all students need to learn how to compute. But that's not sufficient. For example, if students are very proficient in computation, but they don't understand the meanings of the concepts of all of these algorithms, then they're not going to be able to solve real-world problems. And again, that's the reason why we learn mathematics, so we can use it in our day-to-day lives. So let's take a look at an example to just illustrate this point a little further. Suppose we have the following real-world situation, which is certainly commonplace. Suppose your monthly bills are $1,500 and you want to know how much money you're going to pay in bills over the course of a year. So this is an example of a real-world arithmetic problem. Now, you could have a student who is very, very proficient in computation and that can compute 1,500 times 12 with ease. However, if a student doesn't really understand what multiplication is, then they might not even know that 1,500 times 12 is the proper arithmetic needed to solve this problem. And so you can be very proficient in computation, but if you can't interpret a given real-world situation to arrive at the correct computation, then it's going to be useless. Okay? So that's what we're going to do in the next few clips, is we're going to examine each of the 4 arithmetic operations, and we're not going to focus on computation now. We're going to focus more on definitions, models, and interpretations, properties that these operations satisfy, and then we will focus on computation. Okay? So we're going to start with addition, because addition is the simplest of all of the operations. So addition is simply an operation, or an operation I should say, that combines 2 numbers together to make a sum. 2 numbers are sometimes called addends or sumends together to make a sum. And so we can start by just talking about simple computational ways that students can learn their so-called addition facts. This is one of the first things we need to learn about addition, are the so-called addition facts within 20. If you recall our last clip, we actually have already talked about the addition algorithm. Might seem a little bit out of order. It was just natural to talk about the addition algorithm in the context of our chip models. But one of the key skills in learning the addition algorithm is the so-called addition facts within 20. Because again, remember, each step of the addition algorithm requires a 1-digit by 1-digit addition problem. So we sometimes call these addition facts. So what we want to focus on now is, what skills can we use to learn our addition facts? Well, most students first learn addition at a very early age by so-called counting on. This can either be on fingers or pictorially on a number line. So as an example, if we wanted to consider the addition problem 5 plus 2, oftentimes students will learn how to solve the addition problem 5 plus 2 by using a number line. So the first addend or sumend refers to where you start on the number line. So if we are adding 5 plus 2, then we would start at 5, and then we would count on the other addend, in this case 2. So if we count on 2 from 5, we get to 7. So we see that 5 plus 2 is equal to 7. So this is pretty much how every student learns how to add the first time that they're encountered with addition. Now, a number line is a very useful arithmetic model. Sometimes we call it a measurement model. And if we think about a slightly more abstract version of a number line, then we get a bar diagram. And bar diagrams are going to be central to the way that we are going to solve word problems in these clips, and the way that the word problems are solved in Singapore using the model drawing technique. So an example of a bar diagram could illustrate, for example, let's just say 62 plus 37. We could simply use a bar, because we would not want to count out on a number line 62 places and then count on 37 more places. That's just very inefficient. So we would slightly abstract the number line, blow it up a little bit, and we could have something that looks like this. The answer, of course, we're going to denote with question marks. So we could illustrate 62 plus 37 with a bar diagram like so. Okay, so this is a couple of ways to pictorially illustrate the operation of addition. And these types of pictures, these bar diagrams, are going to be really useful when we start solving word problems that involve addition. Now, we mentioned a couple minutes ago that one of the key skills in learning the addition algorithm is single-digit by single-digit addition problems, what we sometimes call addition facts. Oftentimes, these facts are taught purely by memorization. So if you think about that, that can be very, very daunting. The way that I learned these addition facts way back when was I was given a sheet of paper with the numbers 0 through 10 along the top, and 0 through 10 down the column, all the answers filled in, and I was told, memorize all the answers, right? Now, in total, that's 121 different addition problems, because there are 11 numbers across the top, 11 numbers down the side, 11 times 11 is 121. So that is 121 facts to learn. That would be imposing for anybody, let alone an early elementary school student, okay? So what we want to do instead is we want to develop some so-called thinking strategies that students can use to lessen the memorization load that they will have to take on to learn these facts, okay? And what we these thinking strategies are simply based on so-called properties of addition. There are certain properties that the operation of addition satisfies. And if we can become fluent in those properties, then we can use them to our advantage when we are asked to tackle our addition facts. So let's just talk about addition properties for a minute or two. Now, these properties have kind of official adult-sounding words. It's maybe not necessary that students learn these words. However, in some standardized tests, these words, exact words, are used. So, one property that addition satisfies is what is called the commutative property. The commutative property essentially says that it does not matter in which order you add two numbers, you'll always get the same answer. So, for example, 5 plus 3 is exactly the same as 3 plus 5. Now, when students are first shown these properties, a good way to introduce these properties to students is through discovery. Let them come up with properties like this on their own. You can give them a bunch of computations where they see that problems like 5 plus 3 and 3 plus 5 have the same answer, or we could just illustrate it with a simple word problem. We know that addition is the act of combining two numbers together to make a sum. So for example, let's say Mike and I wanted to order a pizza, and I have $5 and he has $3. And if I put my $5 on the table first, and he puts his $3 on the table next, that might illustrate 5 plus 3. But it's quite clearly we have the same amount of money if he were to put his $3 on the table first, and then I were to put my $5 on the table second. So it really doesn't matter in which order we put our money on the table. It does not matter in which order we add two numbers. That's what we refer to as the commutative property of addition. The associative property of addition tells us how to handle addition of more than two numbers at the same time. I mean, if you really think about it, if you were given three numbers to add, let's say 2 plus 4 plus 7. You can really only add two of these at a time, right? So if we were just proceeding left to right, we might say, okay, first we're going to add 2 plus 4, and then we're going to add 7. Now, in mathematics, when we give priority to an operation, we denote that with parentheses. So if we were going to add the 2 plus 4 first, we would put a parentheses around the 2 plus 4 to signify that that's what we're going to do first. Okay? Now, it should seem obvious that if I were to add 2 plus 4 and then add 7, let's say we brought someone else in to contribute to the pizza. I put my $2 on the table, Mike puts his $4 on the table. We do that first. Someone else comes in and puts their $7 on the table. Then we're going to have the same amount of money that we would if maybe Mike put his $4 on the table, the other person put their $7 on the table first, and then I throw my $2 in on the table. Right? It's clear that it doesn't matter which order or which way we combine our money. We're going to have the same amount of money regardless of what order we apply the operation. This is what we mean by the associative property. So if you do 2 plus 4 first and then add 7, you get the exact same answer as you would if you were to get 4 plus 7 first and then add 2. Now, again, these names, while they are the proper terminology that mathematicians use, they're not really intuitive to elementary school students, meaning they don't really convey what's really happening. I mean, the word commutative is not really going to tip off an elementary school student to the fact that, oh, I can add two numbers in any order. Really what's happening is if you combine these two properties together, the upshoot of it is that if you have a long string of numbers, it doesn't matter in which order you add them. So really, these properties combine say a list of numbers may be added in any order. In fact, in the textbook we use here at Worcester State by Tom Parker, he calls this the any order property of addition, which is really describes what's happening. If you have a list of numbers, you can add them in any order. We actually have one more property of addition that is called an identity property. Identity in general means, in the context of an operation, what do you have, or what number in this case would we add to a given number so that it does not change? That number is 0. So for example, 4 plus 0 is equal to 4. Again, this property should be easy to convince students of as well. If I put $4 on the table and you put no dollars on the table, then we have $4 in total, right? Adding 0 does not change a number, does not change a quantity. Okay? So these are our properties of addition. Now, how can these properties be used to help us solve problems over in this list? Right? These 121 facts that we encountered, that we talked about a few minutes ago, how would our properties be used to help us whittle this list down to a more manageable number? Well, there are several thinking strategies, and what we can, actually, let's leave this up. What we can see right away, even without really thinking too hard about this, is that any column or row, because of the commutative property that involves 0, shouldn't really require memorization. All it takes is understanding of the identity property. Anytime where 0 is one of the addends, we should have the number right away. That should not require memorization. Any column that involves a small number like 1 and 2, well, this is how we first learned to add as children anyway, right? By counting on small numbers. We can do this on our fingers, we can do this in our heads pretty easily. So any addition problem that involves a 1 or a 2 should be a pretty straightforward one as well. But notice what the commutative property does is it allows us to not only consider the problems where our second addend is a small number is easy, but now a problem like 7 plus 2, for example, that we might do by counting on, we now realize that that is equivalent to the problem 2 plus 7. So the answer is the same, so we don't have to devote any more memory to 2 plus 7 if we already know 7 plus 2. Okay. There are several more thinking strategies that we can apply to kind of whittle down these facts, and there's an attached PowerPoint that will illustrate some of those. So see the PowerPoint for some further thinking strategies on how to tackle our addition facts.